Okay, welcome everybody to this press conference on tsunami early warning and earthquake forecasting advances and challenges. And we have here Stefano Tinti from Bologna and John McCloskey from Ulster, from the University of Ulster. Stefano, I believe you will start.
Yeah.
Okay, thank you.
Okay, thank you very much. So welcome to everybody. I start this presentation. We really had two distinct presentations, but we decided to have one after the other in this order. This could have been also changed, but it's not relevant in this. I've got the topics I like to talk and I like to touch are these three topics concerning the main problem that we have in tsunami sciences and the tsunami applied sciences, so not only for the theory but also for the application, especially in view of forecasting and the tsunami early warning systems, so the performance and the efficiency of the tsunami early warning system. So the problem is that of tsunami generation mechanism. What are the causes of tsunamis? I prepared a number of slides, but certainly I will skip some of them just to go and to focus on the main points. And then there are problems with the long-term tsunami predictions and problems with the short-term tsunami predictions. Within the long-term tsunami predictions, I put all the stuff and all the activities that goes under the name of tsunami scenario, the preparation of inundation maps, all what is needed to really devise and promote long-term policies for coastal protection just in the long term. For instance, how to establish what are the most appropriate evacuation routes, for instance. So this is really in a certain place that can be affected and managed by tsunamis. Second, the short-term tsunami predictions are really the tsunami prediction that have to do with the emergency, so with the tsunami early warning. So there is a tsunami in place, so we are afraid that there is a tsunami in place, and so we have to do something in order to launch the alert to the population on the coasts. And so these are the topics that I like to touch, and certainly I like to underline what are the weakness of today's research and what are, of course, in the same sense, the problems that are awaiting for us for the solution in the next future or in the future anyhow. So concerning the tsunami generation mechanism, not always is clear. So this can be just the conclusion of that, but I like to make some arguments and so to specify better what is not always is clear. And so we've got certainly this is the geographic distribution of tsunamis. They are very rare events, anyhow, the large tsunamis at least, even though we have a number of tsunamis every year, or at least every a number of years. Usually we have a number every year, a few of them. Every year we have some small tsunamis everywhere in the world. And this, of course, is related, very much correlated with the tectonic activities. So certainly the tectonic processes, especially in the margins that are convergence margins or destructive margins, not constructive margins, these are the places where tsunamis are generated around the world. But of course we are interested here, especially in this conference, and with tsunamis that have to do with our region, so the Euro-Mediterranean region, and we have some non-constructive, of course, margins within the Mediterranean, but we saw that historically there are many tsunamis that have been generated far from the subduction zones that are the zones that we know that are the most prominent, the most favorable for tsunami production. So there are a number of places apart from this is a subduction zone, so it's good to expect tsunamis here, but in other places where there are earthquakes and here, we had in the past large tsunamis that are not exactly attached to this kind of mechanism. And the cause of tsunamis are clear. There are most earthquakes, landslides, so I'm trying to be quite ready and quite fast on it. But there are also tsunamis related to landslides, to volcanic eruptions, also to some meteorological special condition, but let's forget for the moment this, and also unknown causes of tsunamis that in our catalogs probably are related to landslides, submarine landslide tsunamis. But let's consider that most of the tsunamis are related to earthquakes, and just to go also to jump to the last part of my very short presentation, consider that today all the tsunami early warning systems are focused only on generation by earthquakes and not to the others. So if there is some other tsunamis generated by some marine landslide or volcanic eruption, this will not be covered by today's tsunami warning system. No one of the tsunami warning systems today operating in the world. The tsunami generation mechanism is quite clear. By an earthquake, there is a displacement, an offset, displacement of the seafloor, and this displacement of the seafloor causes the mass that is above it to change position, and so creates the first wave, and from this is also related to the subduction zone in this cartoon, in this scheme, and that applies to the Sumatra case. But just to go, so the problem is we know roughly what is the mechanism of tsunami generation by earthquakes, and the idea should have been this one. If we know the earthquake, the characteristic of the earthquake, and from the characteristic of the earthquake we can infer the area where there is a displacement, a permanent displacement upward or downward of the seafloor, and we have the possibility to estimate the amount of such a displacement and the area and the extent of such a displacement, we are in a possibility, this should be the idea, to infer what is the tsunami size, how big is the tsunami in relation to the... but here starts what is not clear, because if you go to, this is a statistics taken from the shallow Pacific earthquakes, so the ones that are favorable for to tsunami production, and we see that we count the number of earthquakes that are very big earthquakes with magnitude larger than 8. We see that only a minority of them have generated a very big tsunamis. So even though from usually seismic data we are able, not immediately but after some processing, to make some estimates on the slip, so how much on the fault the blocks have moved, and indirectly to infer what is the displacement of the seafloor. Not always the tsunami that is generated is in relation with this amount. So generally the larger the slip, the larger the seafloor displacement, the larger the tsunami, but this correlation is not so strict, and so we have a number of tsunamis that have been generated on by earthquakes that had a source slip that was not so relevant, and vice versa. Not all the big earthquakes generate tsunamis. The number of false alerts, in a sense, jumping to the last part of the talk, is could be very high if we rely only upon the data that are related to the earthquakes. And so this statistics, so the difference between the number of events and the number of the generated or large generated tsunamis, of course, increases, so the discrepancies increases very dramatically if you go down to the smaller events. And so, for instance, the number of events that go from 6.5 to 7.5 that are exactly, these are in the Pacific, but these are exactly the large earthquakes that we have here in our Mediterranean area, so in Europe. More or less we are here with a few events that are larger than 7.5. Only a very minority of these generate tsunamis. So this is a point. There is some discrepancies between seismology and tsunami generation. So this is the point. And if we go to our example, so in Italy, I come from Italy, for instance, more or less is the same kind of correlation. The earthquake magnitude of the parent earthquake, so the generating earthquake, and the tsunami intensity, that it's not exactly the energy of the tsunami, but it's related to the damage. Anyhow, a large tsunami has, and a large destructive tsunami has also a large intensity. You see that there is a very large spread, and we can see that a magnitude 7 earthquake can generate a very small tsunami with small effects, but even large tsunamis with the larger effects on an intensity scale that has its maximum in Europe to 6. So very large destruction or almost no destruction. So, and this spread, so this dispersion is in the data between magnitude and tsunami intensity is more or less the same everywhere in the world, and not only for the Italian cases, but this can be applied also to many other catalogs. And this is the first point. So the generation mechanism, even though from the seismological point of view everything is clear, from the tsunami generation there is something they don't understand yet. Second point, the long-term tsunami prediction. If you want to make long-term tsunami prediction, and so to tell what are the regions that are more prone to tsunami attack because are just facing tsunami sources, you should know something, of course, on the statistics, on the frequency of the sources, and if these sources are earthquakes, you should know, at least from historical point of view or from the new knowledge we acquired in these last years on the tectonic, etc., you should know something on the cause, and some statistics of the cause. But until now, not everywhere in the world, but there are special regions, unfortunately our regions, where if you go back on our catalog and you look at the largest earthquakes that generated the largest tsunamis in our cases, we don't know, or we know very little on the positions of the faults of these earthquakes, and we sometimes not even know if that big earthquake generated such a big tsunamis or the cause of the tsunamis was different. And just not to make a lot of confusion, I want to bring to your attention only three small cases, or three cases, not small, these are important events, that are the biggest event we had in Europe, that is the 1755 Lisbon earthquakes on the 1st of November. And just to tell you, until now we don't know yet exactly what is the fault and what was the fault of this earthquake that was estimated to have a magnitude 8.5, according also to tsunami generation and tsunami. This tsunami was so big that affected not only Portugal, Spain, Morocco, but also on the other side of the Atlantic. This is the only case of transatlantic tsunami, the Barbados, and so the Caribbean area. So this was so big in a sense that was comparable to the Sumatra case, etc. But today we don't know what is the fault, and so if we don't know what is the fault, how we can produce a scenario for the future and make some statistics on that. And the same happened also to other cases in Italy. So the biggest earthquake and tsunami that occurred in Italy are these two. One 1908, so last year many people, of course there have been a lot of celebration, especially in southern Italy, for this big earthquake that killed, they say, 100,000 people, and the big tsunami was generated, difficult to understand exactly how many people were produced by, victims, fatalities have to be attributed to the tsunamis, etc., so figures can be not so much reliable, but anyhow we have 13-15 meter waves, so a big tsunami. And the 1693 we had a big earthquake again in Sicily, in this area more or less, and a big tsunami too, even though a bit weaker. And until now we don't know exactly what was the cause of that tsunami. The earthquake itself, but all the simulation that we can. So there is still uncertainty on the fault. The fault was offshore, the fault was close to the coast, etc. And we don't even know if the tsunami was really generated by earthquake or by an additional landslide that modern geologists or marine geology with new marine survey, etc., try to identify it offshore along the Iberian Plateau. So, just to tell you, there are a number of hypotheses of the faults. We don't even know today the fault, and just last year there has been a paper published on GRL telling that probably it was not the earthquake to produce the tsunami, but was a landslide. That's something I don't believe, and so we sent a comment to the same journal, but anyhow, just to tell you that there is uncertainties on this problem. For the largest earthquakes we had and the largest tsunamis we had. So, if there is such uncertainty, it's difficult to produce long-term prediction if we don't know exactly what are the sources. And how we can build the worst credible scenario on the basis of which we can produce inundation map. This is an inundation map that is produced for Cadiz. Technically, we are able to, through tsunami simulation, to produce inundations. But of course, we need to know what is the most credible scenario to attach to this tsunami simulation. And this is just the uncertainty coming from tectonics and seismology. And last example, short-term tsunami predictions. The short-term tsunami prediction has nothing to do with the scenario, etc. Just we know exactly we are there we have monitoring system to detect the earthquake, but in this case, if we don't know the exact relationships between the earthquake and the tsunamis, we are in trouble. So there is some trouble. Today's tsunami early warning system that are either in place or in implementation are four: one for the Pacific, one for the Indian Ocean, the other for the Mediterranean, and the fourth for the Caribbean. I skipped this part for the Mediterranean, even though it's the one where I'm the chairman of the Intergovernmental Coordination Group that has to, in a sense, to implement this system, but I skipped that. If you have questions, of course, I'd be very glad to answer, but to tell you that the idea will be that there will be a number of regional centers that will be responsible for covering all the area, with different institutions from different countries that will cover this area. You see, this is a possibility that is under discussion today. But the most important thing is, apart from the regional center, everybody should have, and nobody has today, so every country should have its national tsunami warning center if they want to protect their own coast. But the problem that I like to stress, and this is my last slide, is this one. So, because we have a very good seismic monitoring system, so the large earthquake that can potentially produce a tsunami is immediately detected. Immediately means after 2 minutes, 3 minutes, 4 minutes. There is the capability today, even in Europe, to do that. They are doing in Sumatra. So after 4 minutes, we have a lot of knowledge of the earthquake. Possibly the location, possibly the magnitude, not exactly the moment, the focal mechanism, but we can make some inferences. But even though we know everything of this earthquake in 4 minutes, we know almost everything, not everything, but let's suppose we know everything, so at the end, we don't know exactly if a tsunami has been really generated or not. So we need to have sea level monitoring system, and this sea level monitoring system that are just tide gauges. These tide gauges should be there to detect the tsunami if it has been really generated or not. So far, sea level monitoring network is there, so all the systems should have also this one, but this sea level network has been devised so far in a way that is inappropriate, because especially where we are waiting, we have to wait for a very short time to have the tsunami wave just on the coast, because the sources are very close to the coast, so the tsunami attacks within 10-15 minutes. It's very unlikely that with today's sea level monitoring network, that tsunami will be detected in 10 minutes, because the sea level network has stations that are too far from each other. And so this network has to be absolutely densified. And so today, practically, what happens is that the real alert is sent out to all the people only on the basis of the seismic network. So there is a big earthquake, it's offshore, okay, we launch the alert. We don't know if a tsunami has been generated or not. We will learn that only after the tsunami or the possible tsunami has reached the closest tide gauges, that maybe can happen also after half an hour or 20 minutes, that is absolutely too late. So generally we are launching false alert because there is a large proportion. So this is something that should be changed. So this is certainly something that has to be changed, and the idea is that we should detect the tsunami from this displacement of the sea surface. Other possibilities are to add to the monitoring system also GPS systems, so there are many other things to do, but what I want us to stress is this real point. So forecasting of a tsunami can be done if we have to, so forecasting in the sense of the tsunami early warning system can be done only if we have these two legs together. The first leg is the seismic knowledge, and the second leg is the initial sea surface elevation that, discretized on the sea level station, can be obtained only through this dense network of sea level stations that is not in place today. So this is what I wanted. So these are the challenges for the future, and certainly in the future this will be tackled. Other point, of course, I said that before, all the tsunamis that are related to landslides and volcanic activity are not covered. It's much more difficult to make estimates on this, and there is nobody that can tell you exactly since the beginning what is the relationships within the landslide thickness, the landslide volume, and the tsunami size in the same terms as we have for the earthquake. So we are a bit behind with these other additional sources, and so the uncertainty we have with the earthquake are even greater, even larger, if we consider also the other causes. This is everything I wanted to tell.
Okay, I'm going to come back to many of the points that Stefano made, but whereas he comes at it from a tsunami expert position, I would consider myself more expert in trying to understand earthquakes and how we can get to grips with the problem of saying useful things for people about earthquakes. And that has involved me in multidisciplinary work which involves tsunami generation, because some of the most exciting earthquake science at the minute is being done in a place south of where the 2004 tsunami earthquake ruptured the boundary of the plates between the Indian and Australian plates and the Eurasian plate, the famous Boxing Day earthquake. So the area that I'm now working in most is an area where the problems are seismological, but there are very close links to tsunami generation, and the threats to dense populations along the Sumatran coast are very high. The potential for a greater disaster than the 2004 earthquake is real, and it's been well documented. So I'd like to just start off, and I'm going to try and just make a couple of very, I think, important points, and maybe give you some idea of where the best earthquake science is being done, and how this, in the absence of an ability or even a requirement to predict anything, we're able to put very strong constraints on what's possible. And then from that we can move forward to trying to say, put an envelope on the bounds of what are the probable outcomes of the next earthquakes, and that those things can be really useful in terms of planning evacuation strategies and things that Stefano talked about there. So first of all, there is a very, I think, mistaken notion that somehow the holy grail of earthquake science is prediction. I don't see it that way at all. I believe presently that earthquake prediction is a distraction. I can give you a couple of examples of why I believe that presently earthquake prediction is not possible. I'm not saying that it is not that it is impossible. I'm saying that at the present I don't think that it's likely to be an attainable goal in the short term, but I want to use the term earthquake forecasting as the real hope of being able to do really useful things for real people who are threatened by earthquakes, which will happen. Okay. Earthquake prediction involves several numbers that we have to get right. We have to get the location right. 30 or 40 kilometers wrong, and the power of the prediction could almost be worse than not saying anything at all. So if you try to evacuate people from a particular place and you move them 30 kilometers, you get everything else right, but you've got that spatial dimension wrong. You can actually make matters worse. So you need to get the location right. There's no point in predicting an earthquake. You have to say what size it's going to be, because small earthquakes happen everywhere, always. So predicting an earthquake has to involve size. And then it has to involve the time. Now, I'm pretty sure that for the Sumatra examples, that the first two we can do really well on, but the time at present is completely beyond any reasonable understanding of the physics as I see it. We published a paper in 2005, in March 2005, saying that the stress had increased on an earthquake fault, and that fault had not ruptured for 130 years or so, and that therefore another big earthquake south of the 2004 earthquake was made more likely. And that earthquake happened almost exactly as we said. So we said it would be between magnitude 8 and 8.5. And we said where it would rupture, and we said the area that would likely rupture. We got all of that right, but we didn't say the time. So we did not make a prediction. We said, here's an area which is dangerous. Turns out that there's no doubt that, well, I'm absolutely confident at least, I think that most people would agree, that the mechanism that we used to make that forecast was correct. And the earthquake was triggered by the effect that we calculated. But the amount of stress involved in triggering the fourth biggest earthquake for 40 years anywhere on the planet is about that much. If I shook your hand normally, far too high. The stress is far too high. So the earthquake was triggered by a tiny amount of stress, which we could never hope to be able to measure deterministically. In other words, we could never have said, we could never have measured the stress field, and we can never hope to measure the stress field to that degree of accuracy. So we can't say when, but we can say a lot of other things about that area that made that forecast, I think, a good example of a very important type of science. It's about trying to understand the underlying physics of the process and then doing the best that we can to constrain what is likely to happen in the future. So many scientists would not agree with me in my rather strident views about earthquake prediction. That's not the important thing. We all can agree that by doing careful science, we can constrain the possible, and therefore that we can prepare for things that are probable rather than just an outside possibility. Okay, so I'm going to give you a couple of quick insights into some of the work we're doing in Sumatra. There's a lot of really good stuff going on in the conference here this week on the Sumatran earthquakes. There are some reasons why Sumatra has given us unprecedented access to data over hundreds of years into the way the earth deforms around earthquakes. And these insights are telling us they're not giving us information to predict earthquakes. They're giving us information to say what the next earthquakes are likely to be like, and then we can compute, for example, scenarios for tsunamis that help people in the population, the very big cities along the Sumatran coast, to prepare for these events. I'm showing here a very interesting phenomenon. Corals in the Sumatran Forearc Islands grow to the lowest, they can't grow above the water, so they grow to the surface at the lowest astronomical tide, and then they grow outwards in these tabular structures. And when an earthquake happens, these tabular structures are sometimes moved out of the water, sometimes they're submerged again, and the corals readjust to grow back into the right, so that they're right at the surface and not beyond it. And the result is that we're able to measure the deformation in the Earth's crust at particular places over periods of hundreds of years. This is unheard of. The precision of these measurements in some places is as good as modern GPS, which we've only been able to deploy for about 5 years in this area. The coral data is giving us, admittedly sparse because these corals don't grow everywhere, but very accurate measurements of the deformation of the surface. Now, that has allowed us to, coupled with modern global positioning, the stuff that you used in, to use GPS in your car, is able to define the deformations down to millimeters, and we can put all of that together to look at the way the interface between the two plates is stuck. Where it's stuck tight, energy is being stored, and we can expect release of energy in future earthquakes. And where it's not stuck tight, then not only is energy not likely to come there from future earthquakes, but earthquakes propagating and rupturing into that area are likely to be stopped because there is no stress, and it's very difficult to make the rupture continue. So the result of that here is, for example, the distribution of this coupling between the plates, the degree to which the plates are stuck, and a contour of the slip on the 2005 earthquake, magnitude 8.7. And we can see that the coupling distribution really nicely marks out where the slip was on the earthquake. And that's a really remarkable thing, that very detailed knowledge of how the surface is deforming is able to tell us not just where the earthquake's likely to be. So it's white here, that means it's poorly coupled, so the earthquake is unlikely to propagate through here. It's white at the top, again the earthquake is unlikely to propagate there. We measured stresses in this area which were increased, and now we would be able to say that the earthquake was likely to happen with maximum slip in this area under the island of Nias, and that it would likely stop here under these Batu Islands. Okay, so this is not a prediction, because we cannot say when this is going to happen. What we can say is that there has been no earthquake here since 1861. What we can say is that the GPS measurements and the corals tell us that the plates are converging at about 5 centimeters per year. We can say the amount of displacement that took place in the 1861 earthquake because of the displacements on the corals, and therefore in 2005 the plate boundary must be near breaking again. Coupling constants say everything's been stuck tight since then, and now you add on top of that some stress from the neighbouring earthquake, and it's a concoction which leads towards a forecast of a likely earthquake, not a prediction. And that's vitally important. So we're now faced with another map of coupling. This area hasn't broken since 1797. You can see there are some very strong areas of coupling onto this. And the great earthquake in 1833 ruptured this area. And either of these events, if they were repeated today, let's put this in context, and nobody responded at all to the threat of the tsunami, could kill several 100,000 people in the city of Padang particularly, but also Bengkulu. So what we are now able to do is to start looking at these areas of coupling, given the information that we've got from previous large earthquakes in this area, and start putting together really detailed scenarios which allow us to predict a whole suite. It's called a Monte Carlo approach. So you take a whole range of earthquakes which are possible and compute what would happen if they actually happened, and that doesn't give you one event, or it doesn't give you one, I'll not go into that. I think actually, have I missed a slide? This is it, okay. So rather than having one event, this is an accumulation for the city of Padang of 125 events, and you can see that most of the earthquakes, and these are all earthquakes of greater than magnitude 8.2, so they're all very, very large. They're called great earthquakes in seismological terms. Most of them don't produce dangerous tsunamis at all, and this is exactly what Stefano said. The magnitude actually doesn't tell you the tsunamigenic potential of earthquakes, but some of them produce earthquakes or of tsunamis of up to 5-6 meters, and very occasionally they produce tsunamis of up to 10 meters for the city of Padang and for the city of Bengkulu. And now I'm able to go, as I have done, and present these results to the legislature in Padang and say, I can't tell you what the next earthquake's going to be like, but it's probably going to be something in this distribution. And it seems to a group of scientists who were working with this that we're actually concerned about this bunch of earthquakes here. These ones are extremely unlikely, and there are good, solid scientific reasons why we say that. And therefore, biggest chance you won't have a serious tsunami as a result even of these very bad earthquakes. But a 6-meter wave coming into the city is first of all something that if people don't prepare for it, hundreds of thousands of people could die. And second of all, and this is really important, it is something that people can prepare for without having to spend lots of money, without producing Californian engineering solutions. We just need to train people, educate people to the dangers, tell them about the warnings that the ground shakes for a certain amount of time. Again, really solidly based scientific information involved in identifying an area which is really dangerous in terms of future earthquakes, and saying as much as possible as we can say about the type of earthquake that it might be, and then people can prepare for that. So prediction is certainly something that no one would, there is no seismologist who would not like to be able to solve that problem. It is not even clear to me whether it would be better than this type of work. I don't believe it's attainable, certainly not in the short term, maybe never. But even if we could say that an earthquake was going to happen of magnitude exactly right, in a particular place, at a particular time, as Stefano pointed out very clearly, it still doesn't tell us what the tsunami's like. So at the end of the day, even if we were able to say the earthquake was going to happen, we still end up with a whole range of possibilities for tsunamigenesis. So those, I think, are some extremely important points that by developing science, the number of people who are killed in earthquakes in Italy has dropped exponentially over the last 100 years. It doesn't mean that scientists were able to predict the Abruzzo earthquake. I really believe that was not possible. But the interaction between science and engineers in developing reasonably affordable and yet effective building codes, for example, are saving people's lives every day in the absence of this requirement that we should be able to predict something. We know that the spine of Italy will have earthquakes of magnitude 6 or 7. That's going to happen by building buildings that are able to survive in those earthquakes. We save lives. 100,000 people died in the Messina Straits earthquake. If you look at the data over the 7 or 8 earthquakes, big, strong earthquakes in Italy over that 100 years, the total number of deaths has dropped monotonically. It's always getting smaller, and it's not disappeared yet, and it probably never will. But now it's 200 rather than 100,000. And I think that is a really important thing that we have to take away. Science is not about reducing the risk to zero or reducing the uncertainty to zero. It's about trying to describe the problem accurately and interacting then with engineers and government people so that populations are better prepared for these type of things. One last point I would like to make. Oh, that's a bit premature. The end. Yeah, I just want to talk about this technique very briefly. On the 29th of October last year, there's a poster on this afternoon out in the hall. But on the 29th of October, there was a magnitude 6.4 earthquake in the mountains between Pakistan and Afghanistan. We were alerted to this, so I can have a text message sent to my mobile phone from the US Geological Survey that can tell me there's been a magnitude an earthquake over magnitude 6. I can then go online, and within about a half an hour, I'm able to say where the earthquake was, pretty accurately. And within an hour, I'm able to say the type of slip that occurred. We have developed algorithms which are not about prediction again. They're about saying where in the area around that are aftershocks likely to happen. There's another fantastic tool which has been developed not for scientific reasons at all. Google Earth allowed me within 1 hour to plot up this diagram and to zoom in to each of the white dots here, which are not earthquakes, they're buildings where people live. And we were able to identify the areas, and all of these white dots are places where population centres are, which had an increased risk of aftershocks as a result of that earthquake. 12 hours later, another magnitude 6.4 earthquake. So the first one happened here. This is the stress around it. The second one happened there. This is science that has been developing over the last 10 years. It's the type of science which allowed us to identify the area that failed in the great 2005 earthquake. It, as yet, is not being used in practice. And I think that this is a big challenge to scientists, and it's a big challenge to social scientists, and it's a big challenge to politicians, and it's a big challenge to civil defense people, that we start taking this well-developed, mature science and start applying it through proof of concept studies, where groups of people, including scientists and including the end users, start engaging in trying to find out how useful is this type of science. It seems to me that it would be very useful, and Google Earth, incidentally, I can have this beamed throughout the world to every person, and a lot of these people have mobile phones or whatever. Information can be got to them, and we estimated, and this paper was published in Nature Geoscience in March, we estimate that within 3 hours of that earthquake we could have told everybody in all these white dots that they were in areas of particularly high risk of aftershocks. This is the appliance of science to try and address real social problems and not to chase rainbows. This is what it's about. Thanks for listening to me.
Okay, thank you very much, John and Stefano, for a very powerful message. I think we have time for just one question because we have a press conference in a couple of minutes. Anyone would like to pose a question? Otherwise, they will make appointments for interviews, I think. Great. Okay. Thank you very much. Thanks. And for this very nice introduction.